Hello, this is Ben from Chicago Bright, and today we're going over another problem from the 1956 Tokyo University entrance exam. And this time we're going to be looking at one of the questions from the STEM major entrance exam. And again, I think these problems are much more difficult than any question that is normally asked on the SAT or the ACT. But I think that the kind of nature of problem solving that's necessary to solve these problems are very similar. Okay, so to begin with this problem, we have fill in the blank with the correct number. When x to the power of 10 is divided by x to the power of 4 plus x to the power of 3 plus x to the power of 2 plus x plus 1, the remainder is blank x to the power of 3 plus blank x to the power of 2 plus blank x plus blank. So from the looks of it, these blanks are going to be the constants in front of these, and then finally like a remainder constant. Whenever we try to solve a problem like this, I think it is important to kind of understand why they gave us certain information, why it makes sense, and why it doesn't, if that ever does happen. For context, the reason why this is important is generally the SAT and ACT gives a lot of information, and all the information is technically useful, as in there is a reason for why they give you any sort of information. Unless there are certain tests you're taking in which they try to give you irrelevant information to mess with you, most tests are built like this. And I think the SAT and ACT does not try to trick the students in this way. So all the information they give you is going to have some reason. Now, let's understand why instead of it starts at x to the third instead of like let's say x to the fourth or x to the fifth. Well, when we divide two numbers, it always makes sense that if this is still somewhat divisible with what we're left with, then it can't be a remainder because we can still divide by this last factor. So for example, it's the same as saying, okay, if I have, let's say 10, and I divide it by 2 one time, well, I get 5. If I try to divide it again by 2, um, or it has a remainder of, let's say, 0 in this case. So instead, this might not be a great example, so instead let's try something else. Let's try something like 15 divided by 4. So normally we would say this is pretty simple. We divide by 3, 12, we have a remainder of 3. But let's say that we chose 2 instead. So we still have a remainder left of 7. 4 is still going into 7, so we can't just say like a remainder of 7 or something like that, because we can still divide 4 into that. So this is just the same type of problem, where because x to the third means that we just simply can't divide with any number we choose with x to the fourth. That's why our remainder always starts at x to the third. Now, overall, this problem for a lot of people, especially if you're in pre-calc, is probably somewhat trivial because this is just a polynomial long division problem. So all you'd really be doing here is saying x to the fourth plus x to the third plus x to the second plus x plus 1. Divide that to x to the 10th. And then you would say like x to the 6th. Then this would be x to the 10th, x to the 9th, x to the 8th, x to the 7th plus x to the 6th, and then we'd subtract that, and then we would just keep going. And then what you'll actually end up finding is that the remainder is 1. So our answer is just 0, 0, 0, 1. So this part seems rather trivial, but I think that this was not really the intended design of this problem. Granted, it might be just a brute force approach to it. You have to keep in mind with some of these entrance exams back then, there was a huge time constraint. They were purposely making it difficult to finish all the problems within time, because they had to select out a lot of students. So instead of just doing long division, there's actually a much more interesting way of solving this problem. So I'll show you the actual method first, and then I'll try to explain it a little more after. So, okay. So this would just basically state that the remainder of dividing x to the 10th with x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1 would give us a remainder of 1. Let's try to explain kind of what the steps here were. I think some people, especially if they have done competition math, would be familiar with a lot of the notation I used here. But let's kind of go over some of these in case you don't. So the first thing is I used a property saying that x to the 5th of 1 can expand to x to minus 1, x to the power 4, plus x to the 3rd, plus x to the 2nd, plus x plus 1. In other words, x to the 5th minus 1 is divisible by x to the 4th, plus x to the 3rd, plus x to the 2nd, plus x plus 1, by x minus 1. So in other words, because it is divisible, we have a remainder of 0. So all this is stating is if this is divided by whatever's in the mod, so in this case x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1, we get a certain remainder. In this case, our remainder is 0. Now, I'm saying that if I add to both sides, the remainder is increased by 1. So then I get x to the 5th is, it gets a remainder of 1 when divided by x to the 4th plus x to the 3rd plus x to the 2nd plus x plus 1. Now I said next I would square these, and if I square this, my remainder still stays 1 because I'm just doing 1 squared. But then I'm still now dividing by x to the power of 10. So then this ultimately leads me to finding that the remainder is 1. Now let's try to understand exactly why this makes sense. So I usually like to break down problems by trying to use an example that's much simpler and easier to understand. So let's start with a problem where let's say I'm trying to find the remainder of 37 when divided by 6. Now, one way we can view it is, let's say 36 divided by 6 gives me a remainder of 0. So in other words, if I were to use the same notation, we would say something like this. Now, if we say 37, so I add 1 to both sides, then the remainder has to be 1. And this is pretty obvious since we know 36, 37, if we just do a long division here, it would give us the same exact problem. Now, let's try with slightly more arbitrary terms. Or even before that, we can even just square it to convince ourselves this makes sense. So 37 squared is, let's see, 1369. So I would say in this situation, it would still be only a remainder of 1, but let's convince ourselves that this actually works out. So this would just be 2, 12, 16. We can put another 2. We get 49. So then we can put 8, which gives us 48, and then a remainder of 1. Okay. So we convince ourselves with a smaller case, but obviously this is not super arbitrary. So we can also just try with just variables essentially. So let's say that if I say a when divided by b gives me a remainder of 0. So in other words, this will leave me with a remainder of 0. So let's say I can rewrite a. I can say a is the same as saying some constant divided times b. So that's the reason why I would be just left with some number that is fully divisible. So let's say I said a is, or let's say we did a plus 1. Well, if I divide both of this by b now, what happens? Well, c times b plus 1, I can separate into two different terms, and this will cancel out just fine. So I'll still be left with c. But in this situation, I have a remainder, because I have 1 left, divided by b. So my remainder is 1 when I add by 1. So as long as I add by a number that is not b, I will always have a remainder. Now, if we square this, let's say a plus 1 squared, so we have c times b plus 1. If we then, let's say, expand this form, we get something like c times b squared plus 2 times c times b plus 1 squared. And if we divide that by b as well, let's say, we can see that this term will have no problems being factored out. This problem also has no problem, and then we still have 1 squared, which is just the same as saying 1. So we still have that remainder of 1 even after we square. So that's the reason why we can kind of do everything we did here when talking about in more arbitrary terms, or in terms that are just easier to understand. If you have any questions about the explanation, or this problem in general, or perhaps another approach you have to it, feel free to leave a comment down below, and I'm more than happy to respond to any of those. Thank you, and have a good day.